All right, two topics here, maybe three, we'll say. The first is the solubility rules. The solubility rules are written in your study guide. If you look in the study guide, maybe about 3 or 4 pages in, there are a couple of lists of solubility rules. So you can look for those. We'll go over them in here briefly. Then I think I would mention, maybe I might put another topic in here. After having gone over the solubility rules, we'll talk a little bit about precipitation reactions. Okay. And then once we talk about precipitation reactions in general, then we'll talk about molecular reactions, total ionic reactions, and net ionic reactions. These three types of reactions are all different ways of writing these precipitation reactions. In fact, these are 3 different ways of writing most of our reactions in aqueous solution. Okay. All right. All right. So first, the solubility rules. When you look at them, they look fairly complicated, but they're not. There are a couple of rules, just a few rules, and then there are some exceptions that go with them. But the exceptions are kind of interrelated. So once you learn the rules for all of the soluble species, when you get to the insoluble species, those are pretty straightforward, and generally speaking, the only exceptions in the rules for insoluble species refer back to what you've already learned for the soluble species. All right, you'll see what I mean when we go through these. All right, so for soluble species, first rule, all alkali metal salts are soluble, right? So the alkali metals, as you recall, are the leftmost column on the periodic table. So that means anything like sodium chloride, anything if it's a salt of sodium, potassium, or lithium, so sodium chloride, potassium nitrate, lithium hydroxide, so on and so forth. As long as the metal is a group 1 metal, that's going to be soluble. Okay. You can find some fairly complex molecules that may be insoluble that contain sodium, potassium, or lithium. But when we're talking about simple, all these solubility rules are for fairly simple molecules. So for simple ionic compounds, these rules hold pretty well. All right. Second rule, all ammonium salts are soluble. So that means anything like ammonium bromide, or ammonium sulfate, or so on and so forth. Any ionic compound, if the cation is ammonium, it's soluble. Okay. And there are no exceptions to that. No exceptions for the first one either. All right. Third one, all nitrates are soluble. So now we're looking at anions. Okay. So anything that is, if the anion is nitrate, could be sodium nitrate, it could be cobalt nitrate, could be silver nitrate, so on and so forth. As long as the anion is nitrate, that's soluble. All right. Next rule, all acetate salts are soluble. And remember that acetate is one of those polyatomic ions, C2H3O2 with a -1 charge. Okay, so for any ionic compound, as long as the anion is acetate, like copper acetate. Apologize, the handwriting there is not great. Copper acetate, that's going to be soluble. Okay, and again, no important exceptions there. All right, first one with exceptions are halides. Most metal halide compounds are soluble. Okay, so for instance, potassium halides you should recall, is the second to the last column on the right on the periodic table. So the column that goes down from fluorine, chlorine, bromine, and iodine. We don't usually include astatine because that's fairly rare. So those first four things: fluoride, chloride, bromide, and iodide. All of those are going to be soluble. So copper 2 chloride, so on and so forth. Okay, this is the first one that has some exceptions. So silver chloride, right? And if silver has a +1 charge, right, then you need 1 chloride with that. So silver chloride, silver fluoride, silver bromide, silver iodide. Same with lead. Lead has a 2+ charge, so lead fluoride would look like that. And also, I'm not sure how well my purple will work. Now this is a weird ion. This is called mercury 1, but it's a diatomic cation. So there are 2 mercury ions. It has a total charge of +2. All right. And so that means since the mercury has a total charge of +2, we need 2 halides to go with it. So Hg2Br2. All right. Okay, so for any of the halides, they're soluble unless the cation is silver, lead, or mercury 1. Okay. And our last rule for soluble species: most sulfate compounds are soluble. So things like cobalt sulfate, nickel sulfate, iron sulfate, potassium sulfate, all of those are going to be soluble. The only ones that are exceptions are calcium, barium, strontium, and lead. Calcium, barium, and lead sulfate are pretty common. Strontium sulfate is something you're less likely to encounter, but those other 3 are fairly common compounds, so you should recognize those as being insoluble. All the other sulfates being soluble. All right, now let's look at the rules for insoluble species. All right, for insoluble species, most carbonates are insoluble. So that means things like nickel carbonate, insoluble. Silver carbonate. Carbonate has a 2- charge, so you need 2 silvers on that. Right? All of those things are insoluble. Okay. Now here's the thing that I was telling you about. There are exceptions here, but you don't really need to worry about the exceptions because you've already learned this exception. Right? The exception here is that carbonates are insoluble except for alkali metals and ammonium. Well, that was the first thing that we already learned when we were doing the solubility rules. We learned that alkali metal salts and ammonium salts are all soluble and there are no exceptions. So we sort of already know this rule here. We already know that group 1 and ammonium carbonate are going to be soluble. All right. Same thing is true with the second rule. Second rule, most phosphate compounds are insoluble, right? So things like, let's do iron 3, because phosphate has a -3 charge, so that makes it easy. Iron 3 phosphate, let's do calcium phosphate. Calcium has a 2+ charge. Phosphate has a 3- charge. So you have to have 2 phosphates and 3 calciums to balance it out. Calcium phosphate, that's insoluble. Okay, so most phosphates tend to be insoluble, again, except for alkali metals and ammonium, and we already knew that. Okay, so lithium phosphate, sodium phosphate, potassium sulfate, phosphate, and ammonium sulfate. I keep messing up. And ammonium phosphate. Those are all going to be soluble. All right. Most hydroxides are insoluble. So for example, iron 2 hydroxide, insoluble. Cobalt 2 hydroxide, insoluble. Right. Aluminum hydroxide, insoluble. Okay. The exceptions, just like before, the exceptions are alkali metals and ammonium. So group 1 hydroxides and ammonium hydroxides are soluble. And then there are these 3 other exceptions. And these are pretty common, again, especially calcium and barium. So calcium hydroxide is soluble. Barium hydroxide is soluble. And strontium hydroxide is soluble. Although, like I said, a little bit less common. All right. And just one more rule. All right, and sulfides are insoluble. And this is almost all of them, right? So sulfide, of course, is sulfur with a 2- charge. So copper sulfide, insoluble. Silver sulfide, insoluble. Lead sulfide, insoluble. Any other transition metals, insoluble. The only things that are soluble are the group 1, so potassium sulfide and sodium sulfide, lithium sulfide, also ammonium sulfide, right? And these guys, magnesium sulfide, calcium sulfide, barium sulfide, are slightly soluble. I believe in the handout, in the study guide, these are listed as being soluble. I've looked at a couple other references where they're listed as being insoluble. They have kind of a marginal solubility. I'm not super concerned about you memorizing this set of exceptions because they're kind of borderline cases. But you should know this definitely. Most sulfide compounds are insoluble, and always alkali metals and ammonium are an exception. Okay. All right, so let's look at precipitation reactions. Okay, so let's say we've got a reaction of copper sulfate and sodium hydroxide. Okay. When these two react, anytime you've got 2 ionic compounds reacting with one another, you've got an ionic compound and an ionic compound here, you're going to have the same kind of a reaction, and this is called double displacement. It's also called, in some places you'll see it, a metathesis reaction. And metathesis and double replacement both mean the same thing. They just mean switching partners, changing the order. Okay, so what that means is if there's going to be a reaction, the reaction is going to be these 2 ionic compounds switching places. So the copper is going to go with the hydroxide, and the sodium is going to go with the sulfate. Okay. So that's our reaction. our product is going to be copper hydroxide. Now we need to look at this carefully. We're forming our products over here. Copper has a +2 charge and hydroxide has a -1 charge. So when we put these together, in order to make a neutral compound, we need 2 hydroxides. So we get copper hydroxide. And the other product is going to be sodium and sulfate. Again, we need to be careful with the charges. Sodium has a +1 charge and sulfate has a 2- charge. Excuse me. So when we put these together, you know what I'm going to do? Hold on a second. I'm going to put this down here. Think of this as one reaction, but I'm going to put the I'm just going to write it down here instead to save some space. So because sodium is +1 and sulfate is -2, the formula is going to be like that. Okay. All right. Now we have to assign states. Okay. Both of these, the copper sulfate and the sodium hydroxide, were reactions, or excuse me, were solutions that we were mixing together. So we know both of those are soluble. Okay. We also know they're soluble because of our solubility rules, right? All group 1 compounds are soluble, so anything with sodium is going to be soluble. For this one here, the copper sulfate, we know that most sulfates are soluble except for a handful over in group 2, calcium and barium and strontium. Okay, so those are both soluble. For our products, okay, sodium sulfate, that's easy. All sodium compounds are soluble, so that's going to be aqueous. Okay, copper hydroxide, go back to our solubility rules. One of the solubility rules is that most hydroxides are insoluble. Okay, the exceptions are group 1s and ammonia. This is not one of those exceptions. So that means copper hydroxide is insoluble. So this is going to form a solid. Okay. All right, now that we've got that done, we need to balance everything. And if you look at this, I think this balances fairly nicely if we just put a 2 here. Okay, so this is our reaction. And again, you can think of this as just being one. Think of this reaction as just being written out like that. I wrote it this way just to save some space because I wanted to show you what this looks like. Okay, what this balancing reaction is telling us is that if you mix a solution of copper sulfate with a solution of sodium hydroxide, you're going to get a solution containing sodium sulfate, and copper hydroxide is going to form as a solid. Okay, and when you have a solution and a solid forms in solution, we call that process precipitation. Okay, and we can call the solid in this case, we call this copper hydroxide the precipitate. Okay. All right, and so here's what that would look like if we have a little test tube and we put some copper sulfate in there, we add a few drops of a solution of sodium hydroxide, it'll look like this. Okay, this kind of pale blue color down here is just the color of the copper sulfate solution. But when we mix these two together, this part up here, you can see that kind of chunky stuff. That is the copper hydroxide solid forming where the two solutions mix together. Okay. And that's what a precipitation reaction looks like. Okay. All right. Let's look at another one. All right. And I'll tell you what, I'll let you do this one. Go ahead and pause the video and write the rest of the reaction. See if you can figure out what the products are over here. See if you can figure out what the products are. See if you can figure out what, if anything, precipitates in the reaction, and then balance it. Okay, and then check back with me, and we'll see if we got the same results. All right. All right. So to figure out the products, all I did was I recognized that this is an ionic reaction between two ionic compounds. So they're just going to switch partners. So the lead goes with the iodide and the potassium goes with the nitrate. So the products are going to be lead iodide and potassium nitrate. Okay. Then based on the charges, I made sure that I had the formulas correct. Lead has a 2+ charge here, and iodide has a 1- charge. So the formula is PbI2. Potassium and nitrate are both +1 and -1, so the formula is just KNO3. And then to balance them, because I had 2 leads and 2 nitrates, I had to put a 2 here in the balanced equation. Okay. For the states, I refer back to the solubility rules. Okay. This one over here is easy. All group 1 compounds are soluble, so potassium, anything is going to be soluble, and also all nitrates are soluble. So there are 2 reasons that we know that this has got to be soluble. So I wrote aqueous over here. Lead iodide, most halides are soluble, right? Iodide's in that column over on the right, so that's a halide. Most halide compounds are soluble except for silver, lead, and mercury. So because this is one of the exceptions, this is going to be insoluble and it's going to form a solid precipitate, and that's why I've got the S there. All right, so that's how we would write that reaction. And like before, here's what this would look like if we had a solution of lead nitrate, and then this here, this is a little pipette, and they're just dropping drops of potassium iodide in here. And when the potassium iodide drops hit the solution, it forms this yellow solid. All right, now I want to look at this. We're going to take those same reactions and we're going to write them a little bit differently. Okay, there are 3 different ways to write these reactions. What we've been doing so far are called molecular equations. We're going to write that. We're also going to write a net ionic equation, or excuse me, a total ionic equation and a net ionic equation. Okay. Why don't you go ahead, like last time, go ahead and finish this one here. Go ahead and complete this reaction, write the molecular equation. I'll do the same thing. We can compare our results, and then I'll walk you through the other 2 types. All right, so this is a reaction between 2 ionic compounds, so they have to switch partners. That's going to give us barium sulfate and sodium chloride. Okay. The formulas are right. Barium and sulfate are both +2 and -2, so that's a balanced equation, or balanced compound as written. And sodium and chloride are both +1 and -1, so that's balanced. Okay. We need to include the states. Sodium chloride is soluble. Okay. And barium sulfate, most sulfates are soluble, but there's a small group of exceptions. which are insoluble. Barium is one of those exceptions. So barium sulfate will form a solid. Okay? And then we need to check to make sure it's balanced. It's not quite balanced. We need a 2 there. Okay. All right. So this, as I said before, this is called a molecular equation. And it's called that because we're writing everything as if they're molecules. We're keeping those cations and anions together. Okay. Now we know from previous videos when we talked about electrolytes that that's not really what happens in solution. If you have a soluble ionic compound, really those ions break apart in solution. So you have free-floating cations and free-floating anions, right, bouncing around in the solution, surrounded by those spheres of water molecules. Okay, so we can write this reaction in a way that's a little bit more, well, actually a lot more accurate. That says what's really, really happening. Okay, if we were to mix these two solutions together, we wouldn't really have a solution with barium chloride molecules in it. We would have a solution that contains a bunch of barium ions and chloride ions. Okay. And when we make that solution, because of the formula here, each barium chloride is going to give us 1 barium and 2 chlorides. We mix that with a solution of sodium sulfate. Again, that solution doesn't really have sodium sulfate in it. What it has is a bunch of sodium ions and a bunch of sulfate ions floating around. Okay. And again, based on the formula, each sodium sulfate is going to give us 1 sulfate and 2 sodiums. So I should put a 2 there. All right. All right. Now, as for products, this is going to give us barium sulfate. Now, barium sulfate is a solid, so that's a non-electrolyte. It's not going to break apart into ions. This actually does exist as barium sulfate solid. Okay. And then we're also going to end up with sodium chloride. This is an electrolyte, so it's going to break apart into sodium ions. Oops. I need to put a 2 here. I was thinking about that too. Sodium and chloride. That's an AQ. I apologize. I'm getting really close to the edge of the screen, so it's hard for me to write there. All right. So this equation says we've got a solution. We mix these together. The solution contains barium ions, chloride ions, sodium ions, and sulfate ions. And when we mix all that together, we're going to get barium sulfate solid precipitating out, and we're going to have sodium ions and chloride ions remaining in solution. That's what this equation is telling us. And this equation is called a total ionic equation because we're writing everything as they really would exist in solution. If something is an electrolyte and it exists as separated ions in solution, then we want to write it as separated ions. If it really does exist as a compound by itself, then we want to write it as a compound by itself. Okay. This, like I said, this is a much more accurate way of describing what's really going on. All right. Now this is a little bit cumbersome because there's a whole bunch of stuff here, and some of it, frankly, is not very interesting. If you look at this equation, we've got sodium ions over here on the left, and we've got sodium ions over here again on the right. So the sodium ions aren't really doing anything. They're just floating around in the solution. At the beginning, when you mix everything together, they're over here floating around, and at the end, on the product side, they're still floating around. So they didn't do anything. Okay, ions in solution that don't do anything are called spectator ions. because it's like they're at a sporting event and they're just watching the action and they're not doing anything. And when we write our next equation, we want to write an equation that only includes what's interesting, what's really happening. And because the sodium is not really doing anything, it's a spectator, we're going to omit that. All right, for the total ionic equation, you want to leave that in, although right now I'm going to cross it out. All right, the sodium wasn't doing anything, it's just a spectator. All right, could you see anything else in the equation that looks exactly the same on the left side and the right side? Something that's not participating in the reaction. At the beginning of the reaction, it's just floating around. At the end of the reaction, it's just floating around. Okay. Yes, I hope you noticed chloride. Okay. We got two chlorides over here, two chlorides over here. They didn't really do anything. They were just spectators. Okay. So we can take this reaction and rewrite it now, focusing only on the interesting species, the ones that are actually doing something. And what we're left with is barium ions reacting with sulfate ions, forming barium sulfate solid. And this is the most accurate way to write a reaction while you're focusing on the important things. So if we interpret this, what this is really saying is we've got a solution that contains barium ions and sulfate ions, and when they react, they form barium sulfate solid. Okay? The fact that there were chloride ions or sodium ions in the solution is not really important because they weren't doing anything. So we're just going to leave them out and focus only on what's important. And when we write a reaction that way, this is called a net ionic equation. Okay. All right. It's important that you are able to write each of these types of equations: molecular equation, total ionic equation, and net ionic equation, and also that you understand what each of them is really doing, what the advantages and disadvantages of each of those different ways of representing the reaction. Okay. All right. Let's look at another one. Okay. All right. We've got copper sulfate and cobalt sulfate and potassium acetate reacting. All right. Go ahead and figure out the products and balance the molecular equation, and I will do the same thing. All right, so I have as my products cobalt 2 acetate and potassium sulfate. Potassium sulfate, most sulfates are soluble and all potassium compounds are soluble. So I know that's soluble. And cobalt 2 acetate, all acetates are soluble. There are no exceptions. So I know that's soluble too. All right. Is it balanced? I believe it is. 2 potassiums. Oh, I need to put a 2 there. All right, now it's balanced. So that's our molecular equation. We've got our reactants, we've got our products, we show what's happening, but we're writing everything as if they exist as molecules. And in aqueous solution, that's not really quite true. Okay, so let's then write a total ionic equation. All right, and anything that is a strong electrolyte, we're going to break apart into its constituent ions. All right, so cobalt sulfate, that's a strong electrolyte. Anything that's ionic and soluble is going to be a strong electrolyte. So there's aqueous cobalt ions and aqueous sulfate ions. Okay. We're reacting that with potassium acetate, that's soluble, so that's going to give us potassium ions and acetate ions. Let me mention something here. When you're doing this, when you break things up, when you've got electrolytes, break them up, but remember, as we said a couple videos ago, the ions, the polyatomic ions, maintain their integrity. So we don't break that up into carbon, hydrogen, and oxygen. The acetate remains together. It just separates from the potassium. All right. And then we need to remember our balancing. There are 2 moles of potassium acetate, so that's going to give us 2 of those and 2 of those. And I'm running out of room, so I'm going to continue this on the next line. And so our products are going to be cobalt acetate, which is going to give us cobalt ions and acetate ions, and potassium sulfate, which is going to give us potassium ions there. Okay. All right. So that's our total ionic equation. And we would interpret this as saying we start with a solution that's got cobalt ions, sulfate ions, potassium ions, and acetate ions. We mix everything together, and at the end of the reaction, we've got cobalt ions, acetate ions, potassium ions, and sulfate ions. Okay. All right, we want to write the net ionic equation. So go back to the total ionic equation and look for spectators. Okay, cobalt is the same on the left and right, so that's a spectator. Sulfate is the same on the left and right, so that's a spectator. Potassium, same on the left and right, that's a spectator. And acetate is the same on the left and right, that's a spectator. Okay. So when we cancel out all the spectators, we've got nothing left, right? Remember, the spectators are the guys that aren't doing anything. The things that are left over are the things that are actually reacting. So by going through this process, okay, we can see that everything is a spectator. That means none of them are actually doing anything. Okay? And this is an example of why this total ionic equation is really important. If you go back to the molecular equation here, this looks like a perfectly fine reaction. And in a sense it is. I mean, it's balanced, right? There's nothing really wrong with it. But by mapping this out as a total ionic equation, we can see that everything is a spectator. So nothing really reacts, nothing really does anything. Okay? So when we go to write our net ionic equation, everything is just spectators. Nothing is really reacting. So for our net ionic equation, we just use the phrase no net reaction. Okay, it means if you take this and mix it with that, pour them together and mix them up, nothing is going to happen. Okay, and that's kind of a fun thing. Before we got to this section, you wouldn't be able to predict whether a reaction was going to happen. If I said mix a solution of cobalt sulfate and potassium acetate, what's going to happen? You wouldn't really know. So you need to have those solubility rules, and you need to understand how to write these molecular equations, total ionic equations, and net ionic equations. And now we know for this particular reaction, nothing happens. That's a really nice predictive tool. All right, let's just do one more. All right, and I'm going to let you do this this whole one by yourself. Go ahead and stop the video and figure out what the products are. Write the molecular equation, total ionic equation, and net ionic equation. Okay. As you're doing it, I'll point this out. Remember that nitrate has a charge of -1, and there are, oops, I meant to put 3 of them here, but I got 2 of them. So this is ferrous nitrate. This is iron 2 nitrate. So note that that iron has a +2 charge on it. That'll be important when you're balancing. Okay, go ahead and write the net ionic, total ionic, and net ionic equations, and see if you get a net reaction or if you get no net reaction as we did last time. Pause the video, take a crack at it, and then we'll compare our results. All right, so I finished the molecular equation. My products were iron hydroxide and sodium nitrate. Sodium nitrate is soluble. All sodium compounds are soluble and all nitrates are soluble, so that was clearly soluble. And the iron 2 hydroxide is insoluble because most hydroxides are insoluble with a few exceptions, and iron is not one of those exceptions. All right, so for the total ionic equation, oh, I'm sorry, I forgot something here. I needed a 2 there to balance that. All right, so for the total ionic equation, sodium hydroxide is a strong electrolyte. So we're going to get sodium ions and hydroxide ions reacting with a solution containing iron 2 ions and nitrate ions, producing there's some iron hydroxide and sodium ions and nitrate ions. All right, so there's our correct total ionic equation. And then for the net ionic equations, we need to go back and cancel out our spectators. Sodium is a spectator and nitrate is a spectator. So our net ionic reaction, net ionic equation, you could write the hydroxide first. People usually write the cation first. But if you wrote the hydroxide first, that would be fine. All right. So there's our net ionic equation. Iron 2 ions in solution with hydroxide ions form iron 2 hydroxide precipitate. All right, terrific. All right, reactions like this will definitely show up on the next exam, so you definitely want to practice those. And I believe there are several examples in the study guide. It's certainly covered in the textbook. All right, so in summary, we looked at the solubility rules. Again, my advice is memorize, first work on memorizing the species that are soluble. And then when you go to memorize the ones that are insoluble, when they have exceptions, usually the exceptions are just the things you already memorized as soluble. So that makes that a lot easier. All right, and then you should be able to write precipitation reactions. Those are all just going to be double displacement or metathesis, which means the cation and the anion are switching partners. and then you need to be able to figure out whether you have something that's solid or not, and then rewrite that as a total ionic equation by taking into account whether things are electrolytes. You know, if something is a strong electrolyte, you want to break it into ions. That gives you the total ionic equation. And then finally, cancel out all the spectators to get the net ionic equation. All right, terrific. This is an important topic, so please do go over this and please practice some of these. All right, I will see you next time.